Anyways, chapter 2 is all about trig. The nice part about trig is now that we've done it once, we understand everything about it. It's going to be significantly easier because you know kind of where everything's going and everything involved. So, first thing we taught you guys in trig, we taught you guys a saying, SOHCAHTOA. Right? This basically told us of our three trig functions. So, stood for sine theta equals the opposite length over top of our hypotenuse. Ka was cosine or cos theta equals the adjacent length over top of the hypotenuse. And toa was our tangent, or tan theta equals the opposite over top of the adjacent. That's the very first thing we went over. Was basically your three trig functions. You don't have to memorize this. You technically get it as a formula, but they're not hard to memorize. With that, we had to memorize our two trig triangles. Again, for basic trigonometry like we have, this only ever works for right triangles. Next semester in grade 11, it gets a bit trickier because we do actually have non-right triangles. However, suddenly these three trig ratios no longer work. So we show it as a right triangle with a square in your 90 degrees. You then have to pick which angle you're labeling the triangle from. For the very first triangle, and again, I like to draw a person, just so we have a point of reference. If we're labeling this triangle based on this bottom angle, across from your angle is the opposite length. Your longest side is always the hypotenuse. And the last one, or the one adjacent to you, is the adjacent length. If we have the same triangle, but instead of labeling it in our bottom right corner, we're going to label it in our top left corner. Same thing happens, except you basically switch your opposite and the adjacent. Because now your opposite length is down below. The hypotenuse should never change. And your adjacent has swapped. It doesn't matter which triangle you use, but if you're trying to find this angle here, rather than find this side and calculate this angle, then recalculate the angle, it's good just to label it with the appropriate angle. Way back in grade 9, you guys learned Pythagorean theorem. And Pythagorean theorem was the very, kind of the first taste you ever had at any sort of trigonometry. And again, it only applies to right triangles. Pythagorean theorem is basically a squared plus b squared equals c squared. However, there was one rule that we stipulated in this. What was it? Say it a bit louder. Got it. C has to be your longest side. So C is basically your hypotenuse. A or B, it doesn't really matter. This could be A, this could be B, you can swap them. It doesn't matter. Only thing that matters is your longest side is C. Just a quick review for Pythagorean theorem, which will now make a lot more sense that we have chapter 4 more or less done under our belt, where if I'm trying to find side C, and I know my bottom length is 10 meters, my side length is, we'll say, 6.5 meters. To solve with Pythagorean theorem, a squared plus b squared equals our c squared. We know that this is c, therefore either of these can be a or b, it doesn't matter. You pick one, we'll go a and b. When we fill in our formula, we have 10 squared plus 6.5 squared equals our c squared. 10 squared we can do in our heads. That's 10 times 10. That's 100. Six and a half we could estimate because we know what's 6 squared and what's 7 squared. 49. So roughly between 36 and 49, it's gonna be like 41-ish. But to get an exact answer, 6.5 squared is 42.25. So we're left with 100. 142.25 equals our c squared. And now, how do we get rid of our c squared term? Yes, Adele? Square root. Square root. So take the square root of both sides. This essentially cancels out our squared value. So we take the square root of 142.25. We know our side length of c equals 11.9, I'll round up, 3 meters. Again, Pythagorean theorem. This should not be new to you guys. Did this last year, probably the year before. The only difference, if you're trying to find a length A or B, rather than when you're adding these, you're basically subtracting, B from C to find your A. Okay. We remember that when it comes to triangles, what do all triangles add up to as far as angles go? Adele? 180. So if I know this side down here is 90 degrees, and this side here is, we'll say, 50 degrees, you can do 180 minus 90 minus 50 to get your answer. Which 180 minus 90 is 90, 90 minus 50 should be 40 degrees. So we know that our top corner up here is going to be 40 degrees. So especially when I ask you guys any sort of trick questions, if there's a missing angle but you know the other two, it's free points just to go up. Simple subtraction. Okay. I'll show you guys one example of simple trig. Then we'll go over the inverse sine, cosine, tan laws, and that's basically chapter 3 for trig, or chapter 2 for trig. Trigonometry wasn't too bad. You guys did it pretty well. If I have I don't know. Mac, do you have a cat? Do you have a cat? You do now. So Mac has a cat. The problem is his cat is stuck in a tree. Yes, you do. Mac's for some reason floating. That's okay. Anyways, Mac has a cat stuck in the tree. Here. He has to figure out how to get his cat out. More or less, he wants to figure out how tall this tree is. He knows that he is going to be standing exactly 20 feet away from this tree. And because he's got a cool little app on his phone, he can figure out exactly the angle he is from the ground to the top of the tree is exactly 17 degrees. We're going to figure out how tall this tree is. So, as you guys are working at this, again, step one is always to label your triangle. So, we know if Mac's here, we're dealing with this angle here. We're trying to find the opposite side, and we know the adjacent. We could put in the hypotenuse, but it's really not relevant for our question. So, we look at SOHCAHTOA, we look at our three trig functions, which uses opposite and adjacent, tan. So, tan theta equals our opposite over the adjacent. Always start by writing out your formula. Then we fill it in. Tan of our angle, which is 17. So tan 17 equals our opposite length, which we do not know, over top of our adjacent, which is 20 feet. Now you need to rearrange your formula to get your unknown by itself. In this case, we simply times both sides by 20, and these two will cancel out. If we had our unknown on the bottom, what do? The shortcut is to swap them. The long method still works out as you basically swap them. Okay. Depending on your calculator, sometimes it's easy to figure out what is tan 17 first. Tan of 17.
Wait, you just took tan 17?
Yes.
Oh my goodness.
Tan of 17 is 0.3057 with a bunch of other stuff behind it, equals our unknown. Or if you get a calculator, you can punch it all into one string. That's fine too. Some you can't. So tan 17 times 20. Our unknown is 6.11 feet tall. So while we were scared that Mac's cat was stuck in a tree, Mac is only, how tall are you, Mac?
I'm like 5'11".
He's like 2.5, 3 inches shorter than this tree. So you could probably just reach up and grab this cat, who we will name
Oh my goodness.
Mr. Mittens. I don't know.
Gerald.
Gerald the cat. I like it.
What about Dave?
No.
I'm a Dave.
You have a Dave?
You have a Dave cat.
Yeah.
Is he fat?
Oh, he is fat.
My sister has a dog named Steve.
Is that the zombie
I think
cat?
we're going on a tangent here.
That's the something.
The last section for chapter 2 was the inverse sine functions. And basically when it came to this, all we had to do...
Wait, can we do that if it was on top?
Pardon?
Can we do one where if the thing was on top?
No, you can just reverse it. We're going to run out of time if I do that for every single one. So instead, we're going to have a triangle. We'll say it is... I'll draw it upside down just for fun.
Just for fun.
The things you find fun.
I think math's fun. Don't you? Everyone was oddly quiet with that.
Did you just ask us if math was fun?
I think it is.
Yes.
My brother thinks math is fun.
Yeah.
But she's like advanced because it's business and stuff.
All right, so in this situation, we're going to try and find this unknown angle. We don't know what it is. We know this long length on the bottom is going to be 44 feet. Actually, we'll say meters, 44 meters. And our height is going to be, well, if that's 44, what's a good estimation for that? That's probably close to 18 meters. And that's all the information you get.
I think I remember.
I think you remember. You do it the exact same way. First thing you have to do is label your triangle, right? Label it based off of our unknown, or this angle. We know this is the opposite side. This is our hypotenuse. Technically, this is the adjacent, but we don't need that. Which formula uses opposite and hypotenuse?
So, sine.
Sine, right? 44, sorry. So, sine theta equals our opposite divided by the hypotenuse.
I don't think.
We start filling it in. We still don't know our theta, so it's simply going to be sine theta equals our opposite, which is 18 divided by 44. And again, depending on your calculator, sometimes it's easier to go 18 divided by 44 just to get your number. The trick here is if you round it too soon, it could mess up your final answer. So sine theta equals, in our case, 0.40909 repeated. Okay. Now, you have to go on your calculator and find the inverse function, right? So right above your sine, cos, and tan, you should have sine -1, cos -1, tan -1.
And then don't we type in 0.409?
You type in inverse sine, sine -1, of that 0.40909. 40909, all of them. Or you could, in this calculator, actually put in your fraction, 18 divided by 44.
There's too much glare.
Too much
You
glare.
can see. I can't see.
How's that?
They got it right.
There you go.
And again, this calculator, and yours loads a little different.
Yeah.
I'm not gonna-
When we take the inverse, what ends up happening is you basically swap out, and it now becomes sine negative 1 of that 0.40909 repeating, and you swap your theta. So your theta would be, what do we get, 24.5 or 15 degrees, like so. And that was basically all of chapter 2. All of trig you guys can do. I could make it a bit harder by giving you guys kind of a weird example with multiple triangles, but the trigonometry itself doesn't change. Everything about that, pretty straightforward. Okay, chapter 3, factoring. Your guys' favorite. Yeah. So, go write this down. Factoring.
Might need to go a little bit slower to understand.
Pardon?
Might need to go a little bit slower to understand.
Well, we'll see how slow I can go.
3 in there.
Oh, yeah.
The nice part is I am recording this. So in theory, you could go online afterwards and pause it, review it, pause it again. What are you looking for, sorry? I need a piece of paper. Hang on.
Wait, can we?
All right, so factoring.
No.
Back in grade 9, Aiden, that can wait. Back in grade 9, you guys did usually some sort of expanding with polynomials. And depending on who you had as a teacher in grade 9, sometimes it was simple, sometimes it was advanced. If it was something like 8x minus 2, when you expand this into your bracket, you would turn into 8x minus 16. That'd be close to grade 9. In grade 10, we amped it up a little bit by giving you guys bigger expressions, usually polynomials. It could have been
Do you mean 8x minus 16, not 8m?
yeah, it should be x. So for polynomials, usually we start out with binomials, something like x plus, 3 times x minus 6. Okay? Some of you guys learned FOIL. Some of you guys learned just to expand it. As long as every term inside your bracket multiplies every other term. So this x multiplies both x and negative 6. And this 3 multiplies 6 and, x and negative 6. X times x turns into x squared. X times negative 6 turns into negative 6x. 3 times x turns into 3x. And 3 times negative 6 turns into what? Negative 18. Perfect. So, we then combine this all into 1. We have an x squared term that's taken care of. Negative 6x plus 3x turns into negative 3x. And we get negative 18. So, that was very basic expanding. The only way I can really make this harder, if I make this trinomial, which nothing else changes other than the fact that you're multiplying into a bigger term. I gave you guys a fun test question where it's like a 4 quadnomial times trinomial.
I remember that. It was dumb.
It's a great question. All right. When it comes to factoring, there's very simple factoring where you just pull one thing out. So if we had where we ask you to simplify something, simplification, basically if you had 16m squared minus 24m minus 16, it's technically considered factoring because you're pulling stuff out, but all we're really doing is we're breaking something down by simplifying it. 16, 24, and 6. What can we pull out of all three of those terms?
2,
2 would work. What's better?
3.
4. Keep going. 8. 8's the best one.
Dang it.
If I pull out an 8, what's 16m squared divided by 8?
2m squared.
2m squared. And what is negative 24m divided by 8?
3.
3m.
Yes.
And what's negative 16 divided by 8?
2.
2.
Negative 2.
So if I pull out an 8, it's the biggest thing I can take out, the most common, or it's the largest common multiple I can pull out of all those. And this
And
is
that's it.
essentially simplifying and breaking down your...
What if you brought up a negative 8?
Technically, you could do that, but then you'd have a negative 2m squared term, which you don't want to have a negative squared term.
Okay.
So you technically could. It will not show up on your test, and I might make fun of you. So. Okay, after that, we have simple factoring, or simple factoring. They're usually one step. It's not too bad.
Okay, so this is the answer. I'm just gonna-
That's it. That's the answer. When it comes to simple factoring, we know it's simple because we don't have a term in front of your squared term. So, if I give you guys x squared plus 12x plus 20, we know it's simple because there's no coefficient in front of our x squared term. We like these. These should be, on a test, these should take you maybe 30 seconds, if that. If it's multiple choice, you can usually just reverse the math easily as well.
So what do you pull out from this?
So, remember that we need two things that multiply to 20 and add to 12.
I was like, put it at 12.
So you could go out by writing out all the different multiples of 20. So we have 1, we have 20, we have negative 1, negative 20. What did we say, 2 and 10?
Yep.
2 and 10. And as soon as you get the right answer,
Okay.
you could keep going, but I wouldn't. You're basically going to write, in this case we're dealing with x's, so it's going to be x and one of our multiples, positive 2, times x, and our other multiple, which is positive 10.
Okay.
There's someone not happy in the hallway. We could, how could you check your answer for this?
You would just do the
Just expand it, right? Pull it out, kind of what we did up there. So the nice part is in theory on this test, you can tell me exactly what you're going to get because you know which ones you got correct. And that's your final answer. Okay. When it comes to complex
just make it hard.
factoring, there's just more steps involved. So with complex factoring, you are going to have a term in front. And again, the first thing you always want to try to do is if you want to try and simplify this and pull everything out, because if you can make this a simple factor or a simple trinomial, it makes your life a lot easier. It's much quicker. Unfortunately, 4, 20, and 9, we can't pull anything out of that. So with complex factoring, you take your first term and your last term and multiply them together. 4 times 9, what is it?
Wait. Can we first write that down so that we can steps?
You have your steps in the factoring manual and in your notes. This is just a big chapter review, just going to jog your memory. Okay?
So
What's 4 times 9?
4 times 9 is. Yeah,
36.
I was gonna say.
Okay. Now we have to do the same thing. Think of which multiples multiply to 36, but add up to 20. So go through all your multiples. In our case here, 136, 2, 18 and 2, I think works.
Yeah.
18 and 2. So now we cannot just jump to the step where we write these two out. We actually have to break apart our 20x. So when we rewrite this, we're going to write 4x squared, breaking apart our 20x into 18x.
We don't write. Do you not break up the 4x squared?
No, we don't. just your 20x. So we break up 20x into 18x and 2x plus 9. It doesn't matter which order these are in. If you reverse the order, you still get the same answer.
And
Okay. Now, you look at your left side and your right side. Treat this as two separate entities. What can I pull out of 4x squared and 18x? I know I can pull out an x.
2.
2 works.
2x.
2x works. So, what's 4x squared divided by 2x?
X.
It's just 2x. Good. What is 18x divided by 2x?
9.
Just 9. Perfect. Now remember that what we're trying to get here in our other term is 2x plus 9. We have to pull something out, but if we want to remain 2x plus 9, what are we going to pull out? It's easy.
1.
A 1. Usually it's not so quick. Usually it's like a 5 or a 6 or something else. So when I pull that out, I'm going to be left with 2x plus 9. Our final step is we have to combine. So take the two things you pulled out. In our case here, we have a 2x and a 1. So 2x plus 1 is one of our terms. And then one of the terms that was the same. So 2x plus 9. Okay. Again, how can I check if this is correct?
Then
You could expand it out and just check and see. Hello. It's not too bad today. Alrighty. So, we're going over simplifying, simple factoring, complex factoring. There's a couple of special cases that show up quite a bit, and while it is possible to do it without knowing the quick way of doing it, it does make life not so fun. Perfect squared or perfect trinomials. Basically, the first thing you want to realize is your first and last term perfect squares. So if I gave you guys 25 x squared minus 20x plus, we'll say 4. 25x squared minus 20x plus 4. We realize that right off the bat, both 25 and 4 are perfect squares. Before you do anything else, you stop and say, oh, hey, it's a perfect square trinomial. You take the square root of the top. So, what's the square root of 25? Turns into 5. What's the square root of x squared? X. Good. What's the square root of 4? 2. Now, the trick with these ones is figuring out... We don't deal with the square root of 20x. We're just looking at the first and last term. The trick with these ones is realizing if it is negative times negative, positive times negative, or positive times positive. A couple of key factors here. If we don't have a middle term, we know that we're going to have a positive and a negative because they cancel out that middle term. In our case here, because our middle term is negative and our last term is positive, this must be a negative and a negative. If this was a positive and a positive, it'd then be a positive and a positive.
Right, so okay, so let's negative.
The next simplest way we can look at this, if I had 25x squared plus 4, same thing happens, right? Square root, front and back, we know it's going to be 5x and 2, 5x and 2. Because there's no middle term, one must be positive, one must be negative. Because when you actually expand it out, it would cancel out your middle terms.
Wait, so what if they were both negative? Would it be a positive or a negative or a negative or a positive?
I do not believe it's possible.
So the whole speed.
No.
But
Because
what's
yeah,
the
then you'd
positive?
have at the last end you'd have a negative times a negative. Like it's you couldn't get the negative number
Okay, well,
while
what if-
having a
What if they were both positive? Would it be positive, positive?
yes.
I just wanted to verify that.
Now that you have me saying that, I'm gonna try to think and see.
Wait, what?
I'm not gonna say it's impossible because I do believe you can figure out a situation. Let me think after class. I'll write a couple out. I'll probably find one that can be. We'll see. Okay, that was basically it for chapter 3.
So what do we do now?
Sorry,
So what do we do now?
we're doing chapter 4.
How do I just do it?
Yeah, hang on.
Thank you.
I'll pause the video. But anyways,
It's like an hour, I think. No, there's no limit actually.
is there a limit? Good, because we might do a 45-minute video. Usually I do a lot more pausing if you guys write this down. This has just been a lot of information. Okay. I don't usually edit it much. Chapter 4. This was all about radicals and roots.
Oh, I can help. So radicals and roots?
Yeah. At the very beginning, we talked a lot about estimation and estimating roots. Nowadays, it's not as useful as it used to be. But if I gave you guys and said you must estimate the square root of 30, we're remembering that an estimation is what?
Educating.
It's an educating. It's not just a guess, right? If I'm going to guess how tall Munir is, if it's a guess, he's 8,000 feet tall. If it's an estimate, it's probably close to like 6 foot. So,
How do you always use the word level?
Munir sits right in front of me.
He also uses
And Mac. It's because it's a straight line right there.
or we just
Although neither of them wear a hat. That's why I usually draw Aiden if I have to draw someone with a hat. Alright. If I had to estimate the square root of 30, you think of the nearest perfect square both above and below it. So below 30 would be the square root of 25, and above would be the square root of 36. What's the square root of 25?
5.
5. Square root of 36? 6. Is 30 slightly closer to 25 or 36? It is ever so slightly closer to 36. So, well, it's 5 away from 25. And, oh, no. Sorry, it's closer to 25. Which means right in between 5 and 6 is 5.5. We're slightly closer to 25. I'm going to guess 5.4, give or take. I remember that our squiggly lines are estimations. And the actual number, the square root of 30, hey, look at that, 5.47. Not a bad estimation. Okay. Oh, weird. Hang on. The very first thing we did is we started classifying numbers. I'm also going to spend a bit more time on chapter 4 just because your test is on Monday. So, the very first classification of numbers we have are natural numbers. Natural numbers are the ones we teach little kids. They're very simple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Nothing too complicated. There's no zeros, there's no negatives, there's no decimals. It's just whole basic numbers.
So, no.
No decimals, no fractions. Okay. After natural numbers, we taught them whole numbers. Whole numbers include all natural numbers, but we also include 0. So it would be like 0, 1, 2, 3, 100. After whole numbers, we then taught you guys integers. And integers, I think that's probably close to grade 5. We start talking about negative numbers. So you could have -4, -3, 0,
You run out
1,
of space.
2, 3,
Sorry, chapter 4.
all the way up to 100.
Including
Includes negatives.
no decimals.
No decimals yet. After integers, we taught you guys rational numbers. Basically, rational numbers are any number that can be written as a fraction.
Does that include decimals?
Yes. Well, because 0.75 as a fraction would be 3 over 4.
So it's everything. It's rational except for pi.
No.
Except for repeat.
If it can be written as a fraction, it is rational. Hang on. So any number that can be written as a fraction. There is a couple of stipulations with this. So 4 can be written as a fraction, because that's 4 is simply 4 over 1. 0.25 can be written as a quarter, or 1/4.
What about 0.0?
Technically, any decimal, hang on, technically any decimal that has a repeating or a terminating decimal point is considered rational.
Wait, what's
So
repeating?
terminating could be like 0.339. It stops, right?
What if it goes on for like 20 decimals but it still stops?
If it still stops and doesn't repeat, or if it still stops, it is considered rational.
What about 0.99999?
Hang on. If it repeats as well, repeating also counts as a rational number.
Well, then what doesn't count?
Everything else.
What? There is no else.
Yeah, there is.
No, pi is not repeating. That's rational.
Okay, well,
I spelled
other than
decimals
pi.
wrong. Also repeating decimals. So like, just like Aiden said, so if we had 6.9999 repeating, that repeating would be a rational number.
Okay, so then what isn't the rational number?
Something
So
like this.
irrational numbers are everything else. Pi, anything that's not repeating. Yes.
Wait, what if it's 0.393939?
Is it repeating? Then yes.
I can think of
Bro, you have these guys in mind.
Take your time. Give me my calculator.
In my computer.
The best example we have is pi, right? Because pi never stops.
But then it's
It also never repeats.
okay. But then what's a number that isn't pi that is irrational?
Just punch in a bunch of numbers and divide it by a bunch of numbers.
Well, that's-
It won't repeat.
But then it terminates. So
Here.
it's,
We'll make life easy. We'll just Google the list of irrational numbers because there's quite a few.
I would like that because I think.
The last thing I want to do is teach you guys like the wrong things. See, this video is called Irrational Numbers. Math is fun.
Can we watch it?
We watched that in the last 10 minutes.
Or right now?
Maybe.
This.
Yeah, you need to educate this fool.
How about this? 22 divided by 7. Oh, wait a minute.
That would be
It's 3.142.857.143.
but
It terminates.
Bro, just because it doesn't fit on the screen doesn't mean it doesn't keep going.
You're getting awfully aggressive about this. How about this? Take the square root of 2.
It's a square root.
Okay. Square root of 2 is 141421356. So
and it'll keep going.
It's not turning. It ends.
Your calculator will usually put a line above it, or it'll just round. So if it's like 3.888559999, it stops it like that. It'll usually say, hey, it's rounding for you.
Okay, so like.
But how do you know this like actually isn't just the
I think you guys are overstressing this.
terminated right?
Well,
I'm going to make the examples really
couple
easy.
of answers on the homework wrong because this is weird. There we go. Look, there's a sine arrow that keeps going.
All right, irrational numbers.
I hate this. Irrational numbers so weird.
Irrational numbers are where all the fun starts.
I'm gonna write dumb numbers because they're dumb.
I don't know about that.
With everything else. So pi and everything else.
If it's not rational, it's irrational.
The irrational numbers.
Basically just non-repeating decimals.
Back to the main point here. The second part for chapter 4, we talked about simplifying your radicals. Okay, this works really well because it actually ties a lot into your factoring we just did. Whenever you multiply a radical, it has to be of the same degree. So a square root times a square root, totally okay. A cubic root times a cubic root, also okay. You cannot, however, times a square root by a cubic root.
Wait, so square root? Square root is good. A cubic root times a cubic root is also good. This is a square root multiplied by a cubic root.
Aiden, while it's nice to have you vocalize your thoughts, many people do not appreciate it. Maybe keep them internally.
Especially if they're not in the same section. So
Yeah.
they're working with these things.
So, when we simplify radicals, I'm going to go over probably the best method for it. There are multiples, but if you want to know the other ones, go back to your notes. Probably the prime factorization. So, simplifying radicals. Let's go with square root 80. That's an easy one. When you're simplifying a radical, you're basically breaking it down into its simplest terms. You're trying to pull out something to make your radical reduced and or smaller. Okay? If it is a square root, you're going to be making groups of 2. If it's a cubic group, it's groups of 3. If it's a fourth group, it's groups of 4. You start by taking the prime factors of 80. So first prime factor is 2. 80 divided by 2 is 40. We keep going with 2. 40 divided by 2 is 20. Gives us 10. Which gives us 5. 5 is prime, so we have to stop. And again, square root, we make groups of 2. There's a cubic root, it's groups of 3, fourth root, etc., groups of 4. So, this is a square root. Therefore, we're going to pull out groups of 2. 5 is left over, so it remains square root of 5. Now, the best way to think about this is what you've pulled out. What's 2 times 2?
4.
4. What you've pulled out is the square root of 4 times the square root of 4 times the square root of 5. What is the square root of 4?
2.
2.
2 times 2, and then what's the square root of 5? Let's see.
Well, we keep it as a root because we don't want to have it
Yeah,
as a decimal. So,
yeah, irrational numbers.
you could jump and say, well, I'm pulling out groups of 2. It's going to turn into a 2. If you can't, just think backwards. What's 2 times 2?
4.
So the simplified root of the square root of 80 is 4 times the square root of 5.
Ta-da!
For video. So if it is a cubic root, we'd make groups of 3 and going on from there.
Hey, this is my calculator.
So
This time, I'm gonna
we've done that, we've done that.
Wait, there's a 40?
Perfect cubes, same idea. Okay, you can go in reverse, by the way. And in fact, one of the outcomes will spend a lot of time saying, hey, unsimplify this. And if you're given something like, let's go 10 times the square root of 7. So, there's two ways to do this, two thought processes. One, you think of a square root that equals 10. What is it? What square root equals 10?
1.
10, 100.
10, 100?
I said 10, then 100.
I see, I agree. So we know that the square root of 100 equals 10. We can then multiply the square root of 100 by the square root of 7, which gives us the square root of 700 as an answer. You could also say, what's 10 squared? Well, it's 100. Therefore, square root of 100, same thing. Both processes work just the same. It's arguably easier to unsimplify it than it is to simplify radicals.
Yeah, this one seems a lot easier.
Okay, after this, we talked about fractional exponents. We taught you guys 3 different methods. Roots have hats, trees have roots, Danook. All you have to remember is x to the power of a fraction of m over n. If you have a fractional exponent x to the power of m over n, this will then turn into the nth root of x to the power of m. Whatever you need to do to memorize that, I would personally just memorize this formula, but some people have come up with other methods. There's all sorts of ones.
Is the nth root a mathematical term?
If you look at your calculator, actually use x.
The x root.
X root? Kind of hard to say. All right, good example for this. Let's go with 27. 27 to the power of 2/3. Okay. This turns into, we know we're going to have 27 as the base of our root. It's going to be a cubic root, and the whole thing is going to be the power of 2. You could go 27 squared first, but it'd be a lot easier if we take the cubic root of 27 before we take the square root. What is the cubic root of 27? 3. This turns into 3 squared. What's 3 squared? 9. The next day, we talked about negative exponents. So when it comes to a negative exponent, so if I had 27 to the power of negative 2/3, with the negative exponent, we have to take the reciprocal of our main number. So the reciprocal of 27 is what? 1 over 27, right. And now that whole thing is to the power of 2/3. This gets rid of our negative. We then have to expand that 2/3 into both the 1 and the 27. So this turns into 1 to the power of 2/3 divided by 27 to the power of 2/3. The cubic root of 1 is 1, and 1 squared is also 1. And we know that 27 to the power of 2/3 is simply 9. Negative exponents. Your very last thing we learned. The very last thing we learned about were the exponent laws. You should have all of these. I'm going to do a quick summary, just so it's kind of quick. Okay?
Can't see.
You cannot see.
So, exponent laws.
All right. The first law, product of powers. Product of powers was a to the power of n times a to the power of m turns into a to the power of m plus n. Our second law was quotient law. And this stated that a to the power of m divided by a to the power of n equaled a to the power of m minus n. Our third law was power law. We're already at 50 minutes. Holy smokes. This is a long video. A to the power of m. That itself is to the power of n. Is the same thing as a to the power of m times n. Our fourth law.
Product of a power. No, we already have that.
It would be power of a product.
Dang it.
Power of a product is when you have two numbers, a times b to the power of m. This turns into a to the power of m times b to the power of m. Please note they must be multiplying. This does not work if they're adding or subtracting. Law 5.
Isn't it quotient? No, product of a quotient.
No.
Power of a quotient.
Power of a quotient.
Yes. Put that in there. I got one.
Power of a quotient. This states that two numbers, a divided by b to the power of m turns into a to the power of m over b to the power of m. However, b can never be what?
Can't be 0.
Cannot be 0. That's it. That's all you guys got.
Happy can't be
Good luck in the test.